And that proton gradient, if you recall, it goes back in, but it goes back in through a proton pump that is made of two subunits, up and F1 producing the ATP. There's your electron transport chain. So now when you look at our total story, imagine you were burning glucose, all 6 carbons of glucose. The terminal metabolites of glucose are CO2, there'll be 6 of them, and water, there'll be 6 of them also. And of course, it'll have to consume 6 oxygen to do that job. So that effectively, as a summary, here's what we can say. Metabolism produces CO2 and water. CO2 and water. Now, how am I going to handle the CO2 and water? Well, to transport the CO2, we're going to use a key enzyme, which is reversible, a big family of enzymes we call carbonic anhydrases. And carbonic anhydrases, they're going to take the CO2 and water, make this protons plus bicarb. Bicarb becomes the major form of CO2 transport. Okay? And that bicarb represents metabolic CO2. So any changes in bicarb, we're going to call that what? Respiratory or metabolic as a change? Obviously. Sam, we're going to call it metabolic because you see where it came from. It came from your metabolism. It came from Krebs cycle and electron transport chain. It came from CO2 and water produced by mitochondria and carbonic anhydrases, making this bicarb and protons. Protons, of course, well, that's what we're going to link to the pH. And pH has no units, as you know well, and it's defined as minus the log of the proton concentration. Or essentially, pH is inversely related to proton concentration. Bicarb we measure. We're gonna measure, and we're gonna measure in millimole per liter, which is the same as milliequivalent per liter. And what is a normal bicarb? Around 25, Sam, sounds good. So I'll put it like I did on the diagram, around 24. For a normal pH, it should be around 7.4 for blood pH, of course. And then it still leaves us with another story for CO2. When you look at PCO2, that's the gas CO2. PCO2, it should always be directly related to metabolic production, no doubt, but it's also inversely related to what? Ventilation rate, how much we ventilate the lungs. So PCO2, we measure that also, but when we measure it in millimeters of mercury, and normal on average would be around 40. So now the big issue we're going to have is clearly there's a relationship between pH, bicarb, and CO2. And in a way, what I can remind you here is if you had an increased CO2, which is either due to increased metabolic production and decreased ventilation rate. If there's increased CO2, I'm shifting the reaction in that direction, and therefore I raise protons. If I raise proton, I lower the pH. And as I lower the pH, increased CO2 is always going to cause acidosis. And if it's due to too much metabolic production, I'm going to call it metabolic acidosis. If it's due to decreased ventilation rate, I'm going to call it respiratory acidosis. You understand the two terms, metabolic versus respiratory? Yeah? Do notice too, at the same time, every time you increase proton from CO2, what must happen to bicarb? It's chemistry. What has to happen to bicarb?